Okay, today actually we have the master course degree student and also doctor course student for this subject. And today we have the Professor Yuichi Anada from Hokkaido Information University. Actually, this university about the information technology, but how can I say that your previous work is about polymer, especially expert in the polymer physics. So today your topic is about the polymer physics, molecular motion, and property of non-crystalline solid. Maybe it's very complicated for our student, but this is a very good chance to meet you in online. We hope that the next time we hope to see you on site. Okay, please, Sensei, please give the lecture for us. Thank you very much again. So please, thank you very much.
Thank you, Open Club, for very kind, precise introduction of me. And I'd like to share PowerPoint, okay? And oh, it doesn't, sorry. Can you see my PowerPoint?
Yes, Sensei, we can see your PowerPoint.
You can see title and my name?
Yes, yes, yes. Okay. Polymer physics.
Okay, so let's start it. The topic, my topic is polymer physics, and wait a little bit. Especially focusing on molecular motion and properties of non-crystalline solid. Polymer physics, field of polymer physics, very big. Later part of this year, many tourists come to our country or Sapporo city. Maybe this year, since from September, I hope. So HIU is next city of Sapporo city. I'm sorry, it's a Japanese. This line is train railway, and from Sapporo station to nearest station of university, it takes 20 minutes by train, in train. So Hokkaido Information University belongs to EDC Group. EDC Group is a private company and university and school group. And this group has 10 computer schools additional to Hokkaido Information University, and 3 companies. It's called SCC, HIIT, Space Engineering Development. Headquarters located in Tokyo. And 10 computer schools located in many places. This red circle is computer school located here. And Hokkaido Information University is here. And SCC company is a company for service of system, computer system, mainly software system. And HIIT is a laboratory of information technology, and the space engineering development company is concerned with space technology. For example, Earth observation system, space transportation system. It's collaborate with JAXA. JAXA is a Japanese organization to launch rocket and launch satellite. And the International Space Station, this, this International Space Station, this company is one of the support company to operation, like that. So now, from now, I'll talk about polymer physics, molecular motions, and polymer properties. This is agenda of today's talk: introduction, fundamentals of physics, polymer physics, molecular motion and physical properties, structure of polymer solid, research. Finally, if I have a time, I introduce my research. So before start the main story, I would like to talk about here, this one. I recommend students to learn how to get knowledge about science and technology and fundamentals of your major field in your university days. Because we interested in normally in applied research or developmental research to produce new one. But for that, we need very fundamental knowledge, and it's important. Historically, people have developed science and technology for a long time in human history, and human beings has got enormous amount of knowledge in the history. But those knowledges have been selected. Many knowledges disappeared in the history. Only a few knowledge alive up to now. So many knowledges have been selected in the stream of history. So I recommend students in your student days, university days, please study fundamentals and method to get new knowledges. Okay. So about polymer. Polymer, a little bit, I summarize polymer history. Polymer was used for our life, mainly because 19th century. But those days, we don't know such kind of material. We don't know structure or origin of such kind of materials. But 100 years ago, we found structure of such kind of, or origin of such kind of material. For example, rubber, wood, something like that. Those are made from polymer, made of polymer, but we didn't know before that. And in 1999, Japanese researcher Nishikawa found fiber structure of cellulose by X-ray diffraction research. And very big year, 1920, Professor Staudinger published a paper which he introduced concept of polymer, namely very such kind of material made of very big molecule. And after that, 1923, synthetic rubber was synthesized, and many physical, it's focusing on physical aspect. Many things found, many theory and many theory. For example, this 1960 structure of polymer crystal. Polymer crystal is very special. It's not like a low molecular weight crystal. As you know, low molecular crystal can be a single crystal, short range order and long range order, perfect long range order. But polymer, intrinsically, it cannot make long range order perfect crystal, because polymer is, I'll explain later again, polymer is like a string-like molecule, and crystal can be made by this stem fold like such kind of structure. So this structure has many part of defect of crystal. And other findings, for example, high conductivity of polyacetylene found 1977 and like that. So in aspect of polymer history, scientific findings is since only these 100 years. Now we consider about the application of the polymers a little bit. Polymer is used for many things, you know. This is only a few examples. For example, infrastructure. This things is rubber, made from rubber, and this is used for suppression of earthquake. I think Thailand, there are not so many earthquake or no earthquake, I think, right? But Japan, there are many earthquake. So high buildings is something to avoid oscillation, vibration of earthquake. So this is this rubber material used for suppression of earthquake. Or transportation, body material of, I think this is a Boeing 787. This body made from some kind of polymer, carbon fiber, and sports, many sports material, many sports things made from polymer. And automobiles also, this is a tire, and electronics also. You can see IC technology. We use integrated circuit. In integrated circuit, there are many elements. It's made from photoresist. Those materials made from polymer. This is made by company actually, which before I worked. Nippon's own company make such kind of material also. But I hope you remind my talk. Fundamental research is very important. Applied practical research to develop practical material. In those basis of these research, fundamental research is if there's a sufficient fundamental research, we cannot develop intrinsic very new technology or revolutionary technology. I introduced you very small experience of me. When I was a researcher in a company, when I graduated Dr. Course students, I was a researcher, and one of my theme of development is such kind of one. Development of a rubber-like material, which slips smoothly on the surface of glasses. These polymer material used to make such kind of a thing, and it's used in window shield in the door of the car. And this long, can you see this long rubber-like material? It's both sides of a glass, and protect from rain or something else. It's penetrating inside of the door. And but long time ago, these things made from such kind of, so this is a hair-like, many small hair-like material. And so this is because such kind of hair-like thing very easy to slip on the door glass. But bad point of this style of material, rain penetrate into the door. So my development topic is develop this material, not to use the hair-like material, but only rubber-like. But rubber-like thing is difficult to slip like that. So, but it's an order of the top, so I have to make something. In that research, shortly, I summarize shortly. Before applied practical research, I consider fundamental research. I did fundamental research. Applied practical research, typical physical quantity for slipping is coefficient of friction. Friction. But origin of friction, we have to consider origin of friction, and we have to make something to decrease friction coefficient. For that, I considered energy loss. Energy loss, of course, surface energy loss because of friction, but also internal, there's an internal friction, internal loss. This related to polymer, physical properties of polymer. So anyway, fundamental research, fundamental knowledge, based on fundamental knowledge, we can develop applied research. It's my experience, small experience. So we move to non-crystalline solid.
Then say, sorry, please back to your previous slide.
Sorry?
Sorry, please back to the previous slide. Previous slide. もう一つのバックしてください。
もう一つバック。Previous.
はい、そうです。この、
はい、
このスライド、very important for our student and for our research in Thailand, because now in Thailand we focusing on the applied research. So it means that from your experience, the fundamental research is very important before go to the applied research. I agree with you, but if I say, many people don't believe me if you say the same sentence. Many Thai student or many Thai research believe on your side more than me. This is very important. And this slide, maybe I can show your slide in our, how can I say, our meeting and our some meeting that that would like to focus on fundamental research first and then go to the applied research. It's very important for our students and our next generation.
Yes.
It's very good. It's very good.
Thank you for a very good comment, Sorapon.
Yes, because this is you already show that not only the fundamental research and also applied research can be, how can I say, can be matched between university research and company. This is a very strong point and a very, how can I say, the critical point, especially for the IMUT around Thailand. So many people focusing on the applied research only. I think this is very important. Thank you very much for this slide, and you're the second or you're the third slide about the fundamental research. Really important. So thank you very much, Sensei.
Thank you for a very good comment. Not only Thai people, but also Japan or other countries, there is some economical problem. We have to develop economy. So we everyday researchers everyday face to own new practical product. We have to. So we usually go to directly applied or practical research, but in that intrinsically very good product cannot be realized, I think. So if you develop very good development, very good new things, I recommend you like Sorapon Sensei, Ajahn Sorapon. I recommend you again. Fundamental research is very important. Okay. So now main story of today's talk, non-crystalline solid and polymer solid. This is today's topic material. Non-crystalline solid or amorphous solid. What is this? The definition of such kind of material is like this. The atoms and molecules does not organize definite crystal lattice. Crystal lattice is a very regular structure of molecule or atoms. But non-crystalline solid or amorphous solid mainly not make ordered structure. And I already talked about the second one. There is a structural short-range order. Sometimes short-range structure order, but not a long-range order like a perfect crystal. And then amorphous, by the way, amorphous means non-crystalline. It's a language. Amorphous. A negative. Morphous. Capable of making a form. Making a form. So amorphous means cannot make a form. It's the origin of this word. And non-crystalline solid or polymer solid, the typical one is glass, plastic, rubber, gel, and so on. But be careful. Those are not name of material. Those are names of state of material, like liquid, gas, or solid. And polymer makes these states. These are non-crystalline states. Glass, plastic, rubber, gel. Polymer is model system for non-crystalline solid. This topic is in the aspect of fundamental research. Model polymer, the meaning of a model polymer is like that. Polymer has very long characteristic time. It's called characteristic time of a material. We call it relaxation time. Usually use symbol tau. Polymer material, many physical phenomena, has a very long relaxation time. But small molecular material, it can make a crystal, such kind of material, metal or some many materials, salt or something like that, which can make a lattice crystal. Those material has very short relaxation time. So if we investigate transition phenomena, steady state, or equilibrium state to another equilibrium state, material state change is the transition state. In transition state, polymer materials has very long relaxation time, so it's easy to observe, easy to experiment. But metal or some many materials, small molecular material, those materials has a very short relaxation time. So it's very difficult to observe or make experiment about the transition state. So we use polymer materials as model system of long relaxation material. We can research precisely the transition state, what happens in those states. It should be common characteristics in small molecular lattice make material. But such a kind of material has very short relaxation time, so difficult to investigate, difficult to research. So that's why polymer is model system for investigating non-crystalline solid. Okay, it's very important, one of the very important point. So we move to another topic. Polymer. what is polymer? I think many students know about such kind of thing, but I summarize. It's an elementary thing, but shortly summarize. Polymer materials has molecular weight of more than 10,000. Definition of polymer molecule is molecule which has molecular weight of more than 10,000 molecular weight. Generally, polymer has such kind of monomer unit. And monomer unit synthesized as a same monomer unit and make polymer molecule. And length of molecule, if we stretch polymer molecule, several hundred of nanometer, very long. Thickness of a hair, 50 or 100 micron. Polymer, very long polymer is 0.1 micrometer. It's smaller than thickness of hair, but not so small. It's a molecule, so it's a very big molecule. But usually these molecule, natural state, not like this extended state. Generally, polymer stayed such kind of coiled state, like a string, what can I say, string. And so we continue to explain fundamentals of polymer physics. Before that, we consider about heating of material. If we heat solid, this blue particle is, molecule or atom. Solid state molecule or atom make such kind of crystal-like structure, generally, and each molecule or atom vibrate thermal vibration. If we heat solid, thermal vibration is enhanced and very rapid vibration and amplitude of vibration increase. But solid material keep such kind of a regular long-range order structure. Liquid, as you know, liquid is a molecule or atom move very fast, faster than solid molecule. And we heat liquid, of course, it's a thermal motion. Macroscopically, we observe it Brownian motion. And so any state, solid, liquid, both increase volume in heating. I think you know very well about this. And gas also. Gas molecule or atom move very fast, faster than liquid molecules. And in heating, more rapidly, each molecule get a large velocity and volume increase. In heating, there's usual material expansion in heating. You remember this one. Keep remember. summarize again. Usual material, heating, volume increase, expansion. So I hope you think about this one. Question. Rubber band. Do you know rubber band? We can see every day, everywhere, not everywhere, but a rubber band. It's made from polymer, polyethylene, or like that. I'm not a chemist, so I don't know it precisely, but such kind of polyethylene or polybutadiene or some compound. It's a very inflexible one. The question is, if we heat this rubber band, what happened? This rubber band increase length or not? What do you think? I hope you consider about this one. 5 minutes. Sorry, 5 seconds. 5 minutes too long. 5 seconds. Okay. So I can see you video. I can see you video. Sorry. Excuse me, wait a little bit. So I stop slideshow. Okay. Wait a little bit. Wait a little bit. 伸びるか自分か言いやすいように、ここに目印としまして。Sorry, I start again and I share my video. Can you see my face?
Yes.
Okay, so I start this video, but unfortunately I speak Japanese, so I translate step by step. So start. 説明するために、まず簡単な実験をやってみます。で、これ、輪ゴム。はい。This is a rubber ring. 普通の輪ゴムです。Usual rubber ring. 今、何でもいいんですが、手元にある重りを何かぶらされます。I hang on it something on this rubber band. So I think, what do you think after hang on something? It happened usual phenomenon. 伸びます。このゴムを温めたら、ゴムは伸びるか、縮むか。はい。He said, if we heat this rubber increase length or decrease length. That's a question I gave you. So, どうでしょうか。じゃあこれをですね、今実際にやってみることにします。Okay, so he says, let's start heating. で、伸びるか縮むか、before that, 目印としまして、物差しを置いておきます。Before that, he said, to observe a length, he used a scale. Put on the scale. で、このゴムの端のところ、メモリの Can you see the end of rubber band? The scale is 30, approximately 30.
で、これ、場所を見比べてください。で、これを今、ヘアドライヤーで温めてみます。
She started to heating by hair dryer.
で、じゃあ、温めてみます。
Okay, you observe carefully. What happens? First position on the scale here. Now here. About 5 or 6 millimeter shortened. Okay.
少しですけども、縮んでいった様子がわかるかと思います。
Okay, so I'll back to slide. So we found in experiment, rubber band, heating rubber band, it's not increase length, decrease length, not expansion, contract, shrink. It's a typical properties of polymer material. Why does it happen? Polymer material is like this. Molecular structure is like this, as I explained. Blue particle is atom or molecular unit, polymer unit, and green line is covalent bond, and this normally shape of such kind of shape, and each particle move by thermally, and direction of many various direction. And heating, this velocity or vibration increase different direction. Finally, shape change, right picture, like right picture. So heating polymer material volume decrease. This is the reason. Okay. This is very different phenomenon, typical different phenomenon from low molecular weight material. So I summarized again. Usual low molecular material, which easily make a lattice, heating, volume increase. But polymer material, heating, volume decrease. And why low molecular materials volume increase? It's because of each molecule or atom has energetically high state. It's an energetic volume change. But why polymer material in heating volume decrease? It's because of not energetic, but entropic reason. So volume change of a polymer material is entropic phenomenon. It's because of entropy, change of entropy of molecular state. So we move to physical properties of polymers. Do you know this one? I think everyone knows this one. Hair dryer. If you are a researcher in company and you have a topic, your boss ordered you develop good body of hair dryer. What do you think? What do you do it about your research approach? Actually, this problem is my entrance examination program in my company. When
Oh, sensei, very good example. So
yeah.
maybe let's our student give the answer.
Okay.
โอเคนักศึกษาครับมีใครตอบได้ไหมครับวัสดุตัวนี้ทำจากอะไรครับผมลองเลือกเขาให้เลือกว่าจะใช้พลาสติกหรือโพลิเมอร์ตัวไหนชนิดไหนลองฝึกตอบคำถามแกดูครับผมฝึกแสดงความคิดเห็นครับเป็นภาษาอังกฤษครับ
I think about it make of the bakelite is the because it heating reliable.
Sorry, again.
Again.
I think that it bakelite because bakelite is the reliable heating. I think that in the heating in the temperature is high. The polymer it cannot. We think that use the electric use the bakelite.
You think
I think
temperature is an important point because the hair dryer temperature of hair dryer increase, so material of hair dryer body material is strong against heat, right?
Sensei
Yes.
อาร์ตลองตอบดิว่าเป็นใช้พลาสติกชนิดอะไรปิกนี่คืออะไรเบเกอร์ไลท์ใช่ไหม
ครับเบเกอร์ไลท์ครับ
โอเคอาร์ต
ครับผม
ตอบได้ไหมเนี่ยโพลิเมอร์ลองดูดิใช้ภาษาอังกฤษลองฝึกใช้ตอบเลย
ไม่รู้อ่ะอาจารย์
ลองสิถ้าคำตอบนึงตอบไม่รู้ไม่ได้มันเลือกถ้าตอบไม่รู้มันคือ โอกาสเป็นศูนย์ถ้าเลือกพลาสติกมาสักตัวหรือ2ตัวโอกาสมันมีสัก10หรือ 20% ก็ยังดี
ของนักอยู่อาจารย์
แทงเหมือนแทงหวยอ่ะไม่ซื้อก็ไม่ถูกอ่ะ ถ้าตอบไม่รู้ก็คือไม่ซื้ออ่ะซื้อสักเลขอ่ะพลาสติกมีตั้งหลายชนิด
PP เหรออาจารย์โพลีโพรพิลีน
ลองตอบเป็นตอบภาษาอังกฤษได้เลี้ยงประโยคหน่อยฝึก
This is used material is polypropylene plastic.
Polypropylene.
Yeah.
Any other material?
มีคำตอบอื่นไหมครับ Okay, Sensei, maybe just to answer. Thank you, Sensei.
Okay, continue.
This is the how can I say the examination for entrance the company, right?
Yes. I answered this problem in my entrance examination when I enter company.
Yes, which company, Sensei? In Hokkaido?
No, Tokyo. As I explained my academic
Okay, thank
history, yes. I first worked in that company located in Tokyo, Nippon Zeon Company, and I worked in a laboratory of that company. I developed a rubber like sleepy rubber on the glass, that company. So we back to this question, this problem. If two students maybe propose material, polypropylene or like that. I think there are some candidate of the material, but in the situation of developed material, we have to consider several things. For example, environment to use hair dryer, requirement from user, physical properties of material for the body of hair dryer. Environment, what things concretely environment factor? I ask again, no? I explain. I don't have much time, so I explain. I think you know, factor of environment is, for example, temperature. First student, I think he pointed out temperature related thing, or humidity, or external force. In using a hair dryer is in the atmosphere of it's of course mainly in the room, but environmental factor, many environmental factor can affect this material, and so on. Many factors. Requirement, it's hard to soften. So if you use hair dryer, temperature increase. In that case, if body soften, it's not good for user, of course. Hard to break, because if we drop hair dryer, it happening. It's if it's break easily, user don't think it's a good hair dryer. Easy to color. So this hair dryer in this slide is a white one, but there's many hair dryer colored by red, green, blue. So such kind of material can be easily colored, and so on. Already. Physical properties. What physical property related to material? For example, melting point, because high temperature, if melting point is low of this material, it's easy to soften. It's related to a requirement of user, or glass transition temperature. Glass transition temperature, I explain soon later. It's a softened state to hard state. It's change to glass transition temperature. So a melting point related to crystal. Polymer material, difficult to make crystal, but as I explained, slide of polymer history, it make some kind of crystal, but not a perfect crystal. So polymer material, many polymer material has melting point of crystal, but many polymer materials has at the same time amorphous part inside material. It's related to glass transition temperature. So if we have to consider many things to develop material, to choose material of hair dryer. But now we don't have time, so we focus on temperature. In that case, user requirement related to hard to soften. And the physical properties, melting point and glass transition point, both related to temperature. But today, I'm focusing on glass transition temperature. This is a slide for explaining glass transition temperature. Glass comparison of glass and
น้อยๆเดี๋ยวครับมาถึง
sorry, okay. Any question? Okay.
Big ปิดไมค์ด้วย Sorry, Sensei. Okay, please continue.
Okay. So this figure shows horizontal axis is temperature. This axis, volume of material. Melted crystal or polymer material or other low molecular material, both high temperature, at a high temperature, melted state, liquid-like state. If we cool, decrease temperature of the liquid state material, low molecular material, like that, low molecular material, molecule make such kind of structure in cartoon. Volume decrease gradually, but some temperature, volume change immediately, like this line. This temperature, we call it crystallization temperature. Many low molecular material easily make a crystal have this temperature, melting temperature, and only one temperature it change state. This is physically phase transition. It's a thermodynamics. And after that, volume of crystal decrease a little bit, decrease. But polymer material or easily glass making material, from a liquid state, temperature decrease, volume of material decrease, of course, but that doesn't change at one point. It doesn't have phase transition. But some temperature, we call it glass transition temperature. Volume, rate of volume change against the temperature, small, becomes smaller. But this point, there's no phenomenon like phase transition phenomenon. And usually this change, this is a very typical figure. So usually change gradually through glass transition temperature and glassy state. This is a typical property of polymer material. So another physical properties of polymers, it's related to relaxation time. This change, gradual change, it's related to glass transition phenomenon, glass transition temperature. To explain these properties, we usually use Maxwell model. Maxwell model is like this. This shows spring, and this one, we call it dashpot. Properties of spring. Spring is characterized by elasticity, elastic coefficient. It's G in here. And the properties of a dashpot is viscosity. So these things are, for example, I'll show you. Can you see? Spring. This is not a, it's like a dashboard. Viscous property. So if we pull spring first, what happened? Do you think? First, spring longer. Okay, spring longer. This one not change, but can you see change? After first spring longer, and after this one up and spring shrink, contract a little bit. Okay, so there's a time retardation. Not this happened at the same time. First, spring long. After that, after some time, this one change. So I back to slide. This model shows such kind of property. So if we give this model some strain like that. Can you see my picture, my photo, my face? So this means that this figure, this straight line means a constant strain. And stress is this force of, for example, spring. First, stress big in this figure, like here. And after that, this dashpot change, stress of spring decrease. This figure here shows this decrease of stress. It depends on time. If we do it for low molecular material or metal, this change of stress rapidly. Polymer material, this change occur very slow. That's why we can observe this transition state property in experiment or observation. So relaxation time is very important physical properties to consider physical properties of polymers. Okay. If we calculate the modulus G based on this model, we use such kind of equation, but we don't explain. I don't explain precisely this equation, but this function phi t is named called decay function. It express this curve, for example. So the model, Maxwell model, as I shown, this decay function is very simple, exponential minus t over tau. It's called Debye type decay function. If we put this function in this equation after calculation, we get such kind of equation. In here, usually modulus become complex quantity, real part and imaginary part. I is imaginary unit. We shortly write this part, real part, G prime, and imaginary part, G double prime. Omega means angular frequency. So if we give vibrational stress of this Maxwell model, frequency of strain means if we change frequency to angular frequency, it's omega. So omega is an external frequency. So important point is modulus in polymer materials, in other words, long relaxation time material, usually expressed by complex real part and imaginary part. After I will explain you, real part is concern usual elasticity. But second one, imaginary one, related to energy loss, inside energy loss. As I explained, rubber slip on the surface of glass, origin is two friction. There's a two friction. One is a surface friction, but another one is an inside friction. Inside friction make energy loss. It's related to this part. So Maxwell model, we call it sometimes a single relaxation. That model has a single relaxation time. If we calculate theoretically, analytically, modulus, real part and imaginary part against the angular frequency, it shows like this. Imaginary part, real part. And as I explained, energy loss inside material caused by outside external strain or force. Under this GW prime curve area is proportional to energy loss, internal friction. This is an experimental example of a polymer material. It's a PMMA, polymethyl methacrylate. I'm sorry, it's Japanese. Symbol E means also modulus elasticity. Actually, I omit explanation. It's because too precise. G is a shear actually strain and stress. E means like this. Anyway, it's the same intrinsically. So EW prime curve shows the peak, but not clear peak, but right-hand sides are not decrease, not big decrease, but there is a peak. But important point is Maxwell model curve like this, and real observation like this. Can you see a difference of two curves? Let's see, you can easily see the difference. Maxwell model curve is very sharp, but real curve is very broad. Why it's happening? There is some theory, some consideration. One of these is multiple Maxwell model consideration. It's a very simple. There's many Maxwell model, and each Maxwell model has different relaxation time. So such kind of material, in this case for PMMA, this broad curve, to explain this broad curve, this material has multiple relaxation time, and we use it by one consideration, multiple Maxwell model. In this model, we analyze modulus, real part and imaginary part. We use such a kind of quantity, h log tau. It's we use it, we call it relaxation spectrum. It's a very important quantity to explain properties of real material of polymer. So broader dispersion of imaginary part or gradually change of real part caused by broad shape of broad spectrum of relaxation spectrum against the frequency or against the relaxation time. This is another example. But usually, generally, polymers have several peaks of imaginary part. This peak shows this is a polystyrene, typical, one of the typical polymer. This peak shows glass transition. This region material become soft state to hard state, change soft state to hard state gradually. And high frequency side, hard state, glassy state. And low frequency side of glass transition range, the rubber-like state. And more lower region, viscous flow occurs. If we use temperature horizontal axis, it changes different inverse direction, but the same change. It's not too many times in this lecture. So this is a very important diagram. We call it relaxation map. It shows the relaxation process. I show this one. This peak position of frequency change in temperature, depend on temperature. So this peak move if we observe different temperature. So relaxation map shows total image of temperature and relaxation time or frequency. This is very important map to characterize physical properties of polymers. I don't have much time, so very shortly I introduce the structure of a polymer solid. Polymer makes, some polymer make crystal, as I explained, but polymer chain make crystal, so such kind of structure, surface area and core area. Surface area is composed of by folded part of polymer. This structure was found by this electron microscope photograph. And this is a spherulite, we call it spherulite. Such kind of crystal unit, crystallite, together and make a big materials. This is a spherulite, and this small part is crystallite. We call it lamella. And many polymer material, polymer solid, such kind of structure, crystallite, we call it lamella, and between lamella, there's an amorphous state of polymer change. So many polymer materials has a structure, crystalline part, pure crystalline parts, and surface non-crystalline part, and amorphous part. Very shortly, I explain my research, only image. It's a part of my doctor's thesis. It's a nuclear, nuclear magnetic NMR experiment. And I found oxidation of the polyethylene. Polyethylene chain is degraded, and folded chain cut by radiation in the air circumstances. And okay, I omit. Electrical property also similar. This circuit model is similar to Maxwell model. So electrical properties, permittivity, dielectric constant, we call it a permittivity. It also depends on frequency, temperature, and expressed by complex function. So similar model can explain electrical properties. So this is an example of my research in electrical properties. This is apparatus in my laboratory. This is apparatus to observe a very small electric current. And this is electrode I made. My laboratory is not rich, so I made many things by myself. And this is a program to operate that apparatus. My students make this program. It's a graphical programming language. LabVIEW, do you know LabVIEW? It's easy to operate the apparatus like that. This is a program. So this is also my previous research. And recent research. Next month, September, I take part in a conference in Spain. In that conference, I make presentation like that. This is a slide, part of my slide. A polymer material has generally dipole moment, and there is a impurity small molecular ion. It's interact each other electrically, ion dipole interaction. So from this consideration, I estimate size of free space of ion motion like that. So I'm sorry, last part, very rapid explanation. Thank you for listeners. Thank you for audience. Open clap.
Oh, thank you very much, Sensei. And any comments or any question from the floor นักศึกษามีอะไรถามไหมครับสักคนละสักคำถามครับปอเอกก่อนเลยเสียปิ๊กแล้วก็ตามด้วยอาร์ตฝึกถามเป็นภาษาอังกฤษนะครับเสียปิ๊กเอาเลย
Anything you can ask me.
ปิ๊กถามเรื่องอะไรก็ได้
ยังไม่มีครับ
ถามเลย
ยังไม่มีคอมเมนต์ครับ
ถ้าไม่ถามเรื่องนี้ถามเรื่องญี่ปุ่นถามเรื่องฮอกไกโดถามเรื่องอะไรก็ได้ขอให้ได้ฝึกถามมาอย่างไม่จำเป็นจะต้องถามเรื่องนี้ก็ได้เพราะผมเข้าใจว่าพวกเองอาจจะเข้าใจบ้างไม่เข้าใจบ้างอาร์ตเตรียมคำถามด้วยอาร์ตได้ยินไหมเนี่ยเตรียมคำถามด้วย ทำแบบอยู่วะหรือไงวะ
Outside of this lecture content. Anything.
anything ปิ๊กลองถามอะไรก็ได้ถามเป็นภาษาญี่ปุ่นลองสิปิ๊ก
先生天気は北海道どうですか？
good
今日はね、いい天気ですよ。It's a very good weather today. Temperature is maybe approximately 24 or 25. It's good. Very comfortable.
very comfortable
Yes.
good Japanese for our student
Yeah.
actually he would like to go to Japan
Yeah. Welcome to Japan.
welcome to Japan ปิ๊กมีอะไรอีกภาษาญี่ปุ่นเรียนมาเยอะลองสักคำถามหนึ่งอะไรก็ได้คำถามอะไรก็ได้แกบอกให้คืออยากให้ได้ฝึกส่วนอาจารย์ถ้าจะถามรอแป๊บนะครับผมอยากจะให้นักศึกษาลองถามก่อนเมื่อกี้เห็นใครอยู่ในนี้มั้งเนี่ยเดี๋ยวแป๊บหนึ่งพวกอาจารย์กิฟต์เหรอกิฟต์นาทีโอ้นี่มาซังHello, Nima. Sensei, we have one PhD student in the course of energy and materials. He from the Iran.
Iran.
Oh, wow.
Iran, yes.
Good.
Yes, but his major is about the ceramics.
Ceramics.
However, Nima, you can ask him in anything. not only the polymer physics,
Sure.
but also the researcher life or Hokkaido life or
Oh, really? Can I ask?
Or big boss life. Okay.
Thank you very much, Professor.
Anything okay?
So if it's really interesting for me, I just want to know how is the researcher lifestyle in Japan, like in Tokyo?
Tokyo, especially Tokyo.
Yes, like
I'm staying now Hokkaido, not in Tokyo, but in anywhere in Japan, style of a researcher may be similar. So some very, very small number of researchers get big money. My sensei, RNTT. But many researchers like me doesn't have not a big amount of money at that time. So for me, in case of me, as I explained, I make my experiment apparatus. Yeah, this one is I bought this one, but it's expensive. It's also I bought, but I made this one or this one. But it's a long time ago. Now I don't do it. And programming to operate these apparatus, observe temperature of, this is a sample, and observe current of this material. We have to make programming, but I don't have much time for make program by myself. So some student in my lab, he's a very, very clever student. He made programming. And so this is an image of interface of this program. We observe this apparatus for observing electric current, and this is the electrode, and we regulate this program. And so Japanese researchers, maybe many style, but normally, many time stay in university. Maybe late in the night. Ajahn Sorapon also stay in RMTT, but interrupt sometimes to outside to do something. But Japanese researcher always stay in laboratory.
Good. I go with Dr. Vilachai and Dr. Bunya.
Sometimes with me in Thailand.
Yes. Can I come?
Yes, especially in the nighttime, because in the daytime we work hard, but in the nighttime we have to relax with the big boss professor. And actually in the nighttime we get some information from the big boss professor about experience, very good experience for the professor life in Japan.
Many Japanese researcher professors stay in university long time. But me, of course, but weekend, actually I do triathlon.
Oh.
You know, swimming,
running.
Wow. 2 weeks ago, I took part in triathlon race.
Yes, marathon.
Marathon next weekend.
Next weekend.
I'll take part in marathon. 42 kilometers.
42.
Wow.
So
can you see my
strong
face?
You are stronger more than us, especially more than big. เห็นไหมเนี่ยเซนเซขนาดนี้เขายังออกกำลังกายเลยเซนเซ how about your age? 60?
Age?
Yes.
68.
68.
Wow.
But he's still working hard and can go marathon, and also very ski expert. He is a very ski expert. EQ, how can I say? Professional. Yes. This. So it's mean that it's very good for your question. It means that you have to balance yourself, your life, for working, relaxing time, and also you will have the good health with good research, and also good thinking about your brain, about your future, and also your, how can I say, our next generation. Very,
Yes.
very good answer, Sensei. But
And,
this is very, very important for us to
yes. And for me,
growing up with a very good health like you.
and for me, good thinking and good drinking.
Good thinking and good drinking. Okay, tonight we will have good drinking
Yes.
first.
Thank you. Okay. Thank you. Thank you for question. That's all.
Okay, and any question? อาจารย์ท่านอื่นมีคำถามไหมครับเรียนเชิญนะครับผม
Excuse me, Professor.
Yes.
Excuse me.
โอ้พี่เล็ก
Yes.
ขอบคุณครับ
I'm
ขอบ
really,
คุณครับ
yeah. Thank you for your presentation. I have 2 questions.
Yes.
I have 2 questions regarding the hair dryer. So may I miss your, maybe you already answer in your presentation, but maybe I missed sometime. First question is, you said that we have to choose many requirements, maybe from the company or your boss, right? But you said that we have to choose only few, right? Maybe, for example, gas transition temperature, and it cannot be softened, something like that. So it is possible we choose more than that requirement, and how difficult that we have to solve this problem, something like that. Is it difficult to do?
Yes. So this example, I hope you understand importance of fundamental research. In the applied practical research, I was also in company laboratory, so I know very well. This is only a example: temperature, how to soften, glass transition temperature. Of course, how to soften melting point is also related, and we have to consider other factors. External forces, it's related to how to break, and user, for considering user, easy to color, it's very important factor. So in applied research, development research, we have to consider these factors totally. But some product, some factor is very important contribution. For example, in this case, melting point, glass transition, or something like that, and easy to color. It's maybe a region of chemistry, and totally we have to consider totally. But in this example, I emphasize the importance of fundamental consideration. Is it answer?
Oh, okay. Yes. Now I think I understand. And another question is, finally, what material should be used for this body of this dye?
I'm a physicist, so I consider I didn't develop concerning the development of body material of a hair dryer. It's a only example. I related to, for example, as I explained first in this lecture, belt mold, car window shield. In that development, I finally arrived material, PVC, polyvinyl chloride, with some plasticizer. I can't remember now, but some plasticizer. But a very important point that development, small particle of polyvinyl chloride, same material, mother material, same as, and it's I forget the word, a cross-linked polyvinyl chloride, small particle. It's very and in make such kind of car belt mold used to window shield. Factory make it by injection like. So in this process, automatically such kind of small particle of cross-linked PVC in the surface of this material. So in the surface of belt mold, small, very small, microscopy level small particle, real area of contact against the glass decrease. So finally, the friction coefficient small, and rubber-like things slipping on the glass. So it's not a case of hair dryer. But
yes.
If we develop real practical product, we have to consider fundamental knowledge and analyze material, in my case, physically, using a microscope or something like that. And until I arrive that results, I analyze material many times, made experiment many times. And
Yes.
finally, he arrived practical material.
Okay.
Mm.
Thank you, sir. And
Indeed.
one more question.
Oh, yes.
Yeah, for your research about the car window shield, something like that. How you measure the energy? How you measure the energy of the rubber bar like that in experiment? Have you measured the energy?
Do you mean in experiment?
Yes.
Do you mean what kind of experiment?
Please go back to the before the previous slide of this slide. Go back.
And finally, first of all, I consider fundamental property. It's as I explained, surface friction and internal friction.
Yes.
Generally, we consider both things. But finally, in this case, in my case, that belt mold for window shield.
Yeah.
Internal friction, not so important. Finally, I understand. Surface friction is more important. I understand that. But this conclusion can be arrived considering from fundamental research.
Okay. I think time's up. Thank you. Thank you very much, sir. Thank you.
We have an opportunity to discuss more about these issues.
Yes,
Thank you, sir.
yes. In December, Sensei.
Yes.
December ขอบคุณพี่เล็กครับ
ขอบคุณครับ
ขอบคุณพี่เล็กครับขอบคุณครับก็เป็นอีกหนึ่งโอกาสครับที่เราจะเขาเรียกไงสารสัมพันธ์ต่อนะสำหรับนักศึกษาระดับบัณฑิตศึกษาเรานะครับ Okay, thank you very much for today. I think now it's time for lunch, and in Japan is almost 2 o'clock.
Already passed.
Already passed. Thank you very much, Sensei, and for your very nice presentation and your very nice answer, very nice comment for us, especially for our next generation, our student, and also our next generation researcher of the Faculty of Engineering. And finally, we would like to say thank you again to Professor Anada, very good friend, and very long. We have very long history together with you, not only the university.
Very long history, more than 10 years.
Long history, maybe nearly 20 years, right?
20 years.
Yes. But you're still strong. But for Bunyang, Sumonman, Kichon, and me, not stronger than you now. So this is maybe the next the next presentation or the next time we would like to invite you again about the topic. How can I say that? How can you keep your very good health and very good research and very strong cooperation, especially for the international cooperation with nearly 70 years old.
Yes.
This is very important for us because if we already get old, we cannot prepare anything. We have to prepare from this age. เนาะพี่เล็กเนาะ ถ้าไม่เตรียมตั้งแต่ตอนนี้เราไปเตรียมตอนเกษียณเนี่ยลำบากแล้วโอเคเซนเซก็เป็นตัวอย่างที่ดีครับก็คือเป็นรีเสิร์ชที่ดีแล้วก็แกแข็งแรงมากจะ70แล้วแกยังโอ้โห working hard อยู่เลย แล้วก็แกเป็นนักกีฬาด้วยครับนักกีฬามาราธอนนักกีฬาสกีนักกีฬาอีกหลายอย่างนะครับโอเคนะครับ Thank you very much again, Sensei. Finally, we would like to say and say thank you again and again, and hope to see you in Thailand in December.
Yes, I hope so.
Yes, today どうもありがとうございました。
ありがとうございました。
Thank
you, Professor Anada.
Thank you,
Thank you, Professor Anada.
Arigato.
Thank you, sir.
See you in December.
Exit.
December.
Thank you.
Okay. どうもありがとうございました。どうもおおきに先生 โอเคขอบคุณนักศึกษาทุกท่านครับขอบคุณอาจารย์ทุกท่านครับขอบคุณครับและสวัสดีครับอาจารย์ขอบคุณครับสวัสดีครับ